Hello everybody, welcome back to another video. In this video, we'll be introducing the gamma function. We won't be proving any of its properties so far, although I will definitely do that in another video, but we will be looking at a very interesting question that relates to the gamma function, which is 1/2 factorial. And that is the aim of today's video. That is the goal. We have to find what 1/2 factorial is. And this looks like a lot of symbols, but what are we asking here? We're asking what 1/2 factorial is. And the way we'll do that is by looking at the gamma function. And the gamma function is defined like this. So we have gamma of x is defined to be an integral from 0 to infinity of t to the x minus 1 times e to the negative t dt. And how does this relate to factorials? Well, actually, if we have some x factorial, that is actually equal to the gamma function of x plus 1. And another property that we know is that gamma of x plus 1 is equal to x times gamma of x. So with these properties in mind, we will be solving and figuring out what a 1/2 factorial is. And the way we'll do that is we'll first take the gamma of 1/2. And by definition, the gamma of 1/2 will be, because we know that x factorial is the gamma of x plus 1. Therefore, 1/2 factorial will be, the gamma of 1/2 will be negative 1/2 factorial. So in order to get gamma of x plus 1, which is what we want, which is 1/2 factorial, we will need to use the second property here. The gamma of x plus 1 is x times the gamma of x. Right now, our x is 1/2. So therefore, gamma of x plus 1 will be 1/2, because that is our x, times the gamma of 1/2. And that will give us 1/2 factorial. So let's get started, because our end goal today will just be to figure out, to take a half of the gamma of 1/2. So let's compute the gamma of 1/2. We know that here the gamma function is defined by this integral. So what we'll be doing is we're just evaluating that integral. So we have the integral from 0 to infinity of t to the x minus 1, which is 1/2 minus 1 e to the negative t dt. And that is going to be equal to, we can simplify the exponent there, we have 0 to infinity of t to the negative 1/2 of e to the negative t dt. And the way I'll actually write this integral is I'll write it as the integral of e to the negative t over, and then because we have t to the negative 1/2, that's the same thing as 1 over t to the half, and t to the half is just the square root of t. So this is our integral that we have to evaluate. And we see that we have a square root on the bottom. So that seems like a good time to use a u substitution. And we'll work from there. So we can try setting u to be, let's see, the u is the square root of t. So therefore, the u is going to be derivative of a square root of something is always 1 over 2 times the square root of that thing times the derivative of the inside. So the derivative of t is just 1. So that is what we have here, dt. And therefore, dt, multiplying by 2 root x on both 2 root t on both sides, we get 2 root t du. So we can take this to the u world now. This is the integral, and of course we need to figure out the bounds. So this is where we have x is equal to 0 and x is, or where we actually have t is equal to 0 and t is equal to infinity, because our x is what was passed as the input here. It's just a constant. So t is the variable we're integrating with respect to. And to figure out the u bounds, we take the square root of t. So square root of 0 is 0, and the square root of infinity is just infinity, so the bounds remain to be the same. So now we have e to the negative t over the square root of t, and then let's just take this 2 that is here out of the integral, and then we have the square root of t du. And what we see here is that we'll see that this square root of t and this square root of t cancel very nicely. And what we have here is 2 times the integral from 0 to infinity of e to the negative t du. However, the t is not invited in the u world. So what do we do about this? Well, we need to rearrange to solve for e to the negative t in the u world. So coming back from here, we know that u is the square root of t. So therefore, we can see that u squared, because let's just square both sides here. We see that u squared is t. And if we want to figure out what e to the negative t is, let's just raise both sides to the power of e. So e to the u squared is equal to e to the t, e to the t. And all we do here to figure out e to the negative t is just stick a negative sign in front of the exponent, because that is what e to the negative t is. We just put a negative sign there. So this e to the negative t in the u world is really just the integral of from 0 to infinity of e to the negative u squared, that's a key fact, du. And what is this? Well, this is a actually very, very famous integral called the Gaussian integral. And this is not the exact Gaussian integral, but the Gaussian integral is the integral from negative infinity to infinity of e to the negative x squared dx. And guess what that evaluated to? That evaluated to the square root of pi. Yes, a very beautiful answer that involves some complicated math. But what we'll be doing is we'll be using the fact that e to the negative u squared is an even function, because when we plug in negative x into x squared, it'll remain to be x squared, therefore it'll remain to be the same. So what we can actually do is we can see that we have the bounds negative infinity to infinity, and here we have the bound 0 to infinity. So that is really just half of the Gaussian integral. So what we can do is we can actually write this as a half of the Gaussian integral, 2 times a half of the Gaussian integral, which actually evaluates to the square root of pi. So what we see here is that this 2 and this half cancel, and we're just left with the square root of pi over here. And this all comes from the fact that this 2 was here originally, and this half of the integral, half of the Gaussian integral, cancelled with this 2 multiple here. So therefore, the gamma of 1/2 is the square root of pi. And now we know that we are initially trying to find what 1/2 factorial is, and we know that x factorial is the gamma of x plus 1. So what we figured out is what negative 1/2 factorial is. But to figure out what x plus 1 factorial is, or the gamma of x plus 1, which is x factorial, is, we use the second property here, which is the fact that the gamma of x plus 1 is x times the gamma of x. So what was our x? Our x was 1/2. Therefore, the gamma of x plus 1, which is 3/2, is equal to 1/2 times the square root of pi, which is 1/2 times the square root of pi. And that also happens to be 1/2 factorial, because, of course, the x factorial is gamma of x plus 1. So therefore here we can just leave it like this. Therefore, 1/2 factorial is going to be equal to the square root of pi over 2. That is pretty amazing. It's always cool how pi can creep into things where you never expect it, and including the factorials, which is pretty cool. So that was it for today's video, and thank you for watching.